Hi, and welcome back to Understanding Motors. Last episode, we talked about how changing the way you perform PWM switching can affect the efficiency and dynamics of your commutation. However, the commutation schemes we've developed thus far are not the best methods of commutation we could use. But before we can jump straight to the ideal methods, we have to develop some tools so that we can better understand them. So, let's get into it. We're going to start today by briefly going back and changing some of our notation. In episode 5, when we were talking about the magnetic field alignment method of torque, we learned that in order to maximize our torque produced in a brushless motor, we want our induced magnetic field to be orthogonal to and leading our rotor's magnetic field. In the notation I used that episode, the magnetic field vector generated by the stator of the brushless motor will be 90 degrees counterclockwise from the current vector, as shown in the motor winding diagram. However, after releasing episode 5, it was clarified to me that this notation of having the current and magnetic field shown as perpendicular is not the standard method of teaching within the electrical engineering community. And because my ultimate goal here is to provide you, the viewer, with a reliable and easily intuitive explanation of these topics, I read up on it. And both because I don't want my videos to not resemble what you see in your textbook, and because I genuinely think the more standard notation is better for understanding the transformations we're talking about today than the methods I was taught, I've decided to shift my notation. I apologize if this change causes anyone to be confused, but I'm going to do my best to keep things as clear as possible. In previous episodes, we had shown our brushless motor like this, and our Y circuit like this. For the analysis of 6-block commutation, as well as everything else we've talked about so far, this is completely fine. But now we're going to change the look of this Y circuit a little. Instead of representing the phase as a resistor which generates a magnetic field perpendicular to the direction of current, we're going to change this to a coil of wires which generates a magnetic field in the same direction the current runs. The reason we're actually doing this is because it's helpful to have our magnetic field vectors and our current vectors in line with each other. Because at the end of the day, it doesn't really matter which direction the current is physically running, just the direction of the magnetic field induced by that current flow. However, in terms of measurement and control, it's easier to think about current running through phases than magnetic field generated. Now, with this new notation, a current into phase A will correspond to both a current vector and a magnetic field vector strictly to the left. A current into B will produce vectors 60 degrees south of east, and C will be 60 degrees north of east. So, now that we've adopted this more standard depiction of the diagram, let's take a second to think about it. The first thing I want you to notice is that this is a two-dimensional diagram. I know that this is a completely obvious observation, but it's also a very powerful fact. Because our three-phase current and magnetic field vectors can be described on this two-dimensional plane, it's possible to describe the result as a 2D vector. And then we could theoretically generate any equivalent resultant vector from just two phases. And this is the idea behind the Clark transformation. First implemented by Edith Clark, who, by the way, was America's first professionally employed female electrical engineer, the Clark transform describes the move from the A, B, and C windings to the alpha-beta frame. We can largely derive this transformation geometrically, seeing that A points strictly in the alpha direction, B points in the negative cosine 60 alpha, sine 60 beta, and C points in the negative cosine 60 alpha, negative sine 60 beta direction. The Clark transform also includes an external 2/3 multiplier, and this keeps the vectors equal magnitudes on either side of the transformation. I find that this idea is not super clear at first, but a quick example helps to show why it's necessary. If I wanted to run 1 amp strictly from right to left through the three-phase diagram, it will go into A, then, because this is a balanced system which obeys Kirchhoff's current law, it would need to come out of B and C in equal proportions. If we sum this geometrically, this 1 amp sort of gets counted twice. It gets counted once on the way in through A, and then because of the geometry, it gets counted another half of the time when it's coming out through B and C. However, in our alpha-beta representation, we're just talking about the actual current running in each direction. So we'll need to take 2/3 of this current represented by the summation of the ABC frame to get 1 amp. And just so you aren't confused if you see it, there's actually two forms of this transformation. The one I'm using here, which is the vector magnitude invariant version, and another version used for power analysis, which is the power invariant version, and it uses the square root of 2/3 instead of 2/3. So now we get what the Clark transformation says, but it can actually be further simplified. Because once again, the three-phase system we're talking about is assumed to be balanced, and thus it follows Kirchhoff's current law, meaning the current in phase A plus that in B plus that in C must equal 0. By moving some variables around and doing some substitution, we can then see that the current in alpha is equal to the current in A, whereas the current in beta is the current in B minus the current in C divided by the square root of 3. So now we can describe the direction of current and induced magnetic field using the alpha and beta axes, but it may not be immediately obvious why this is helpful. As we previously stated, inducing a magnetic field perpendicular to the rotor's magnetic field produces torque. Meanwhile, if we induce along the direction of the rotor's magnetic field, it will sum with the magnetic field of the rotor, thus either amplifying or weakening it. Well, we just showed how you can describe the equivalent induction of a three-phase motor in two directions. So now we're going to take this two-axis representation and analyze it from the perspective of the rotor. We will do this through what's called the Park transformation. We're going to start by creating another reference frame which will turn with the rotor. By convention, the axes of this frame are referred to as the direct or D-axis and quadrature or Q-axis. The direct axis points in the direction of the rotor's magnetic field, whereas the quadrature axis is 90 degrees counterclockwise of it. So, a magnetic field induced in the positive Q direction will produce a counterclockwise torque. Meanwhile, one induced in the negative Q direction will produce a clockwise torque. Whereas a magnetic field induced in the positive D direction corresponds to strengthening the magnetic field of the rotor, and induction in the negative D direction will weaken the rotor's field. Since the DQ axis keeps the same origin as the alpha-beta axis, we can describe a transformation between the two as a simple rotation matrix. For those unfamiliar, this is basically just a matrix of trigonometric relationships which can take a vector or orientation described in the alpha-beta frame and then describe it in the DQ frame. Thus, the current in the Q direction is negative I alpha sine theta plus I beta cosine theta, and the current in the D direction is I alpha cosine theta plus I beta sine theta, where this theta value is the angle between the alpha axis and the D axis. Okay, so now we have these transformations and reference frames, so let's look at what the actual implications are. First of all, if we want to optimize the amount of torque we're getting per current in, which we usually do, we can say that at any time for a non-salient pole motor, we want our current to point strictly in the Q-axis direction. Note that if we're using a salient pole motor, the optimal direction depends on some other variables and will typically lead our Q-axis a little bit. I'll link a set of MIT class notes that talk about this in the description below for people who are curious. But to keep things simpler, let's presume we're using a non-salient pole motor, and let's run through our 6-block commutation scheme, again using this diagram. Starting off in the center of Hall sector 0 and connecting our phases appropriately, we're initially perfectly aligned with the Q-axis and are optimally generating torque. However, as we move across the remainder of this Hall sector, our direction of current is no longer aligned with the Q-axis. Continuing on, we see that throughout commutation, we are only perfectly aligned with this Q-axis at the very center of each Hall sector. And as we get closer to the edges of the Hall sectors, more and more of our current points in the plus or minus D directions. This causes the amount of torque we're producing to oscillate up and down, and it creates the torque ripple we talked about in an earlier episode. So now we have the Clark and Park transforms in our tool belt. Next episode, we're going to take the ideas we talked about here and work towards developing a commutation method that will smooth this torque ripple out.